Okay, let's unpack this. Imagine you're just floating out there, deep space, total emptiness.
Yeah.
You have a rock, you throw it. Now, instinctively, you know, Newton's first law, you should just keep going. Yeah. Same speed, straight line, forever.
That's the intuition, definitely.
But what if?
Yeah.
What if it didn't? What if in the real universe it actually, like, slowed down
Yeah.
and eventually just stopped?
Okay.
Where did the energy go? I mean, this wasn't some small question. It apparently really stumped people around the turn of the 20th century. Even Einstein.
Yeah, it's fascinating, actually. Einstein, when he was putting together general relativity, his new theory of gravity, he actually thought that energy conservation, that very principle, might be the key.
The key to finishing the theory.
Exactly. The key to nailing down his big equations about gravity. It was seen as, fundamental, absolutely bedrock.
Well, and then, out of almost nowhere, comes Emmy Noether, a mathematician, not very well known at the time. I gather she wasn't even getting paid.
That's right. Initially unpaid. A real struggle for recognition.
And she doesn't just, like, find a mistake. She basically corrects Einstein on this. And in doing so, creates this whole new way of thinking in physics about why anything is conserved.
It's an incredible story. She essentially gave us the why behind conservation laws.
It seems almost unbelievable. Someone fighting just to be taken seriously ends up revolutionizing physics.
It really is. And the setting for all this, it's around 1915, University of Göttingen in Germany. Einstein's there. He's giving lectures on general relativity.
That's been electrifying.
Oh, absolutely. People were excited, but Einstein himself knew there were still pieces missing, big questions. And one of the absolute toughest was proving that total energy was conserved in his new picture of gravity.
So Einstein's wrestling with his own creation, trying to make energy conservation fit. And then another big name gets involved. David Hilbert.
Precisely. Hilbert, a giant in mathematics, he hears about this problem, gets intrigued.
Naturally.
So he dives into the mathematics of Einstein's theory, looking specifically for equations that say energy is conserved.
And what did he find?
Well, he found something. These things called the Bianchi identities.
Bianchi identities.
Isn't that cool?
Sounds technical. What did they actually say?
They did show energy conservation, but, and this is the kicker, only in a universe that was completely empty.
Empty. Like nothing in it at all.
Nothing. No stars, no planets, no dust, just empty space. So for our universe, the one we actually live in.
Which is decidedly not empty.
Exactly. They seem pretty useless. Hilbert was, well, stuck.
Okay, so Hilbert hits a wall with this empty universe equation. And this is when he brings in Emmy Noether, his new assistant.
That's the moment. He essentially hands her this massive, thorny problem. Talk about pressure.
Yeah, no kidding. And her journey to even get to that point.
Yeah.
It wasn't easy, was it?
Not at all. It's important context, really. She wanted to study math at the University of Erlangen, where her father taught. But back then,
Women weren't really allowed.
they weren't officially students, no. She had to get special permission just to sit in on lectures. The academic senate there actually said allowing women would overthrow all academic order. Unbelievable.
It really is. So she was determined. In 1903, she went to Göttingen for a semester, which was a bit more progressive, thankfully.
And that's where she encountered symmetry.
Yes, that's where she first really got into the mathematical ideas of symmetry, especially in geometry, a concept that would become central to her work.
Symmetry. Okay, let's break that down a bit. Like an equilateral triangle.
Perfect example. All sides equal. If you imagine drawing a line from a corner straight down to the middle of the opposite side.
Like folding it in half?
Exactly. And if you put a mirror on that line, the reflection looks just like the original triangle. That line is an axis of symmetry.
And it has 3 of those lines, right?
It does. Those reflections are actions, transformations that leave the triangle looking unchanged.
Okay, makes sense. But symmetry is broader than just reflections, isn't it?
Oh, much broader. Mathematically, a symmetry is any action you can perform on something that leaves it looking exactly the same afterwards.
So for the triangle, you could also rotate it by 120 degrees or 240 or a full 360. It lands back looking identical.
Ah.
So those 3 rotations plus the 3 reflections, those are all the symmetries of the equilateral triangle. They're the transformations that leave it invariant.
Invariant, unchanged.
Yeah.
Got it. How does that apply to something less visual, like a math function?
Great question. Think of just a simple function. It's a graph on a page. What happens if you just shift the whole graph straight up or down? Say add a constant a to the function.
All the a values change. The graph moves.
Right. But now think about the derivative of that function, the slope at any point. What happens to the constant a when you take the derivative?
It disappears. The derivative of a constant is 0, so the slope, the rate of change,
Yeah.
it stays the same.
Exactly. So even though the function itself changed, it was translated vertically, its derivative remained invariant. That's a kind of symmetry, a translational symmetry.
And that one's continuous, right? You can
Yeah.
shift it up by any amount.
Precisely. Unlike the triangle's specific angles or lines, the core idea is an action leaves some property unchanged.
And Noether just ran with this idea, become an expert.
She absolutely dove into it. Over the next decade or so, she became one of the world's leading experts on the mathematics of symmetry and invariance. She eventually got her PhD back in Erlangen, only the second woman in Germany to do so.
Quite an achievement given the hurdles.
Phenomenal. And then she returned to Göttingen, armed with this deep understanding of symmetry, just as Hilbert and Einstein were grappling with this energy problem.
Okay, so back to Einstein's problem. He needs energy conservation to work in general relativity.
Yeah.
He proposes his own fix, right?
He does. He suggests an equation. Basically, it said, add up the energy of all the matter plus the energy stored in the gravitational field itself. That total sum, he proposed, should stay constant, always zero change.
That sounds pretty reasonable, doesn't it?
Yeah.
Total energy, including gravity's energy, should be fixed.
It sounds intuitive, yes, but Noether looked closely at his equation, and she saw a fundamental clash, a contradiction with the very bedrock principle of general relativity itself.
Which was?
General covariance.
General covariance. Okay, that sounds important. We should probably unpack that. It came out of his earlier work, Special Relativity.
Exactly. 10 years earlier, 1905, Special Relativity. That was built on the idea that the laws of physics look the same for anyone moving at a constant speed in what we call inertial frames.
But the universe isn't just constant speed, is it? There's acceleration, there's gravity pulling things.
Right. That was the next step for Einstein. How do you make relativity work for all kinds of motion? Accelerating, rotating, anything. That's the general part.
And he had that famous insight. The happiest thought, the falling painter or window cleaner.
That's the story. Working in the patent office, he imagines someone falling and realizes during the fall, they wouldn't feel their own weight. They'd be weightless.
Like an astronaut in space.
Exactly like that. Drop something, it just floats next to you. It's indistinguishable from being far from any gravity.
That's the equivalence principle, isn't it? Gravity feels the same as acceleration.
Bingo! If you're in a sealed rocket accelerating upwards at 9.8 meters per second squared, it feels exactly like standing on Earth. That was huge. It meant understanding acceleration could unlock the secret of gravity.
But to build a theory of gravity from this, he needed a core rule about how the laws of gravity should behave.
He did. He needed the mathematical form of the laws of gravity to be identical, no matter how you're moving, accelerating, whatever frame of reference you choose.
That's general covariance. The laws don't depend on your viewpoint.
That's the heart of it. The physics has to be the same for everyone, everywhere, no matter their state of motion.
And making that work mathematically required tensors. Sounds complex. Can you give us the gist?
Okay, think of a vector, an arrow. You can describe it with coordinates, right? Like 3 steps right, 2 steps up.
Yeah.
But if you rotate your map, your coordinate system, those numbers, the 3 and 2, will change.
Right, the components change.
But the arrow itself, the actual physical thing, hasn't changed length or direction. Tensors are basically a generalization of that. They're mathematical objects whose fundamental nature doesn't change when you change your coordinate system.
Your components might change, but they change in a specific, coordinated way.
Exactly. Such that the underlying physical reality they represent stays consistent. Einstein needed tensors, so his equations for gravity would have the same form regardless of the coordinates used, to satisfy general covariance.
Okay, tensors ensure the laws look the same. Now, back to Noether and Einstein's proposed energy equation. Where was the clash with general covariance?
Okay, so Noether digs into Einstein's equation, and she spots something. It wasn't using a proper tensor for the gravitational energy part. It used something called a pseudo-tensor.
Pseudo, like fake.
Pretty much. It looked a bit like a tensor, but when you actually tried to transform it from one frame of reference to another, like going from a stationary observer to an accelerating one, it didn't follow the proper tensor rules.
What did that mean practically?
It meant that the amount of gravitational energy you calculated could literally depend on how you were moving. It could appear or disappear just by changing your frame of reference.
Whoa. So energy conservation would depend on the observer.
Mm-hmm.
That completely violates general covariance.
Exactly. It broke the fundamental principle. The laws weren't the same for everyone.
And this led Noether to ask a huge question, didn't it?
It did. She started thinking, what if? What if general covariance itself, the symmetry of the laws under changing viewpoints, is actually incompatible with the traditional idea of energy conservation?
A conflict at the very foundation.
Yes. And she realized that general covariance is a kind of symmetry, a very powerful local symmetry, and symmetry was her expertise.
So she approached it using her knowledge of symmetry, starting simple.
Right. She went back to basics. Imagine the simplest universe. Totally empty, static, not expanding or contracting, just flat, unchanging space and time.
Okay.
In that universe, does it matter where you are? If you do an experiment here or over there?
No, it should be the same. Space is uniform.
That's translational symmetry in space. The laws of physics are the same everywhere.
And she connected that symmetry to momentum.
Directly. Think about throwing that rock again in this empty static void. Because the laws are the same everywhere, there's nothing to slow it down or speed it up differently in different places. It just keeps going. Its momentum is conserved. Noether proved mathematically that this conservation of momentum is a direct consequence of space's translational symmetry. Uniform space means momentum is conserved.
That's amazing. What about other symmetries, like rotation?
Same logic. In this empty universe, does it matter which way you're facing?
No. Direction shouldn't matter either.
That's rotational symmetry. And Noether showed that symmetry directly leads to the conservation of angular momentum.
Yeah.
Spin something, it keeps spinning. Physics doesn't care about orientation.
I'd blown. Space symmetry gives momentum. Rotational symmetry gives angular momentum. What about time?
The big one, time symmetry. In this static, unchanging universe, do the laws of physics change from today to tomorrow?
No, they should be constant over time, too.
Right. And Noether showed that this time symmetry, the fact that the laws don't change over time, that's where the conservation of energy comes from.
Okay, how did she show that mathematically? It involves something called the Lagrangian?
Yes, she used a powerful framework called the principle of least action. The basic idea is that nature is, in a sense, efficient. A physical system will always follow a path between 2 points in time that minimizes a quantity called the action.
And the action depends on the Lagrangian.
Right. The Lagrangian is often defined, simply put, as the kinetic energy, energy of motion, minus the potential energy, stored energy. You calculate this difference at every moment along a possible path, sum it up, integrate it, and that's the action for that path. Nature chooses the path with the least action.
Okay.
Noether then asked, what happens to this action if the underlying laws have a symmetry? Specifically, what if the laws don't change when you shift time forward or backward a tiny bit? That's time translation symmetry.
And what did she find?
She proved, mathematically, that if the action doesn't change under this time shift, if time symmetry holds, then a specific quantity must remain constant throughout the motion.
And that quantity was?
The total energy of the system. Kinetic plus potential. Boom! Conservation of energy is a direct result of time symmetry.
Wow. So it's not just some rule someone made up. Energy is conserved because the fundamental laws don't change over time.
Exactly. She found the origin story for conservation laws.
That's Noether's first theorem, right? Formalizing this connection.
That's the one. Every continuous symmetry corresponds to a conserved quantity. Space translation, momentum, rotation, angular momentum, time translation energy was utterly revolutionary.
But hang on, our universe isn't static and unchanging, is it? We know it's expanding.
Ah, yes, the plot thickens. By the 1920s, astronomers like Hubble were seeing galaxies moving away from us. The further away, the faster they recede, the universe is expanding.
And later we found out it's even accelerating.
Correct, thanks to observations of distant supernovae in the late 90s. So, on the grand cosmic scale, our universe is definitely not symmetric in time. It looked very different billions of years ago, hotter, denser. It will look very different in the future.
So, if the universe lacks time symmetry on the largest scales, what does Noether's theorem say about energy conservation?
It says that energy, and the way we usually think of it as being absolutely globally conserved, isn't. Not on the cosmological scale.
Whoa, so energy isn't conserved across the whole universe.
Not in that strict classical sense. Think about light from the early universe. A photon travels across billions of years of expanding space.
Its wavelength gets stretched, right? Redshifted.
Exactly.
Hmm.
Longer wavelength means lower frequency, which means lower energy according to quantum mechanics, E(h)f. So the photon loses energy as the universe expands.
Where does the energy go?
That's the mind-ending part. It doesn't really go anywhere. It's just lost relative to the expanding space. Because the underlying time symmetry needed for strict conservation is broken by the expansion itself.
So back to my rock thrown in space. It slows down because the expansion of space itself is like doing work on it, diluting its energy.
That's a good way to think about it, yeah. Its momentum and energy decrease relative to the overall expansion. It eventually comes to rest relative to the cosmic microwave background, the sort of frame of the expanding universe. Energy isn't conserved globally.
Okay, that's a huge concept. But
Mhm.
wait, if energy isn't conserved globally, why does it seem to be conserved in, like, my lab? Or when I play pool? Things don't just randomly lose energy here on Earth.
Excellent question. It's about timescales and locality. The expansion of the universe is happening, but on the scale of your lab or even the solar system, and over timescales of seconds, days, years, the change is absolutely minuscule.
So locally, and for short times, the universe looks pretty much time-symmetric.
Exactly. Time translation symmetry holds to an incredibly good approximation for all practical purposes in our everyday experience. That's why energy appears to be conserved in chemistry, engineering, biology, etc. It's only when you look at the universe over billions of years that the lack of global time symmetry really bites.
Okay, that makes sense. So Noether's first theorem explains why energy isn't globally conserved in our expanding universe. But what about the original problem? Energy conservation within general relativity itself. The thing Hilbert and Einstein were stuck on.
Right. That takes us to Noether's second theorem. The first theorem was about global symmetries, like shifting the entire universe uniformly. But general relativity with curved spacetime doesn't really have those simple global symmetries.
Because space-time is warped by mass and energy.
Precisely. But Noether realized GR does have a different, more sophisticated kind of symmetry, local symmetry.
Well, local symmetry.
Think about general covariance again. The laws of physics look the same, no matter how you're moving or accelerating locally in your immediate vicinity. That invariance under local changes of coordinates is a local symmetry.
Okay. And did these local symmetries also lead to conservation laws?
They lead to something related but different. Noether's second theorem showed that local symmetries don't give you strict global conservation laws like total energy is constant. Instead, they give you continuity equations.
Continuity equations. What are those like?
Imagine water flowing in a pipe. A continuity equation describes how the amount of water in a specific section changes. It says the rate of change of water in that section equals the amount flowing in minus the amount flowing out.
So it tracks the flow. It says water isn't being created or destroyed locally in that section, just moving through.
Exactly. It describes local conservation of flow.
How did Noether apply that to energy in general relativity?
She derived a continuity equation for energy flow in spacetime. Think of spacetime divided into tiny patches. Within each patch, the equation says energy flow is balanced, what comes in equals what goes out, plus any change inside. Locally, energy behaves.
But what happens when you try to add up all the patches to get a global picture?
That's where the curvature of spacetime comes in. The curvature, described by Einstein's equations, acts almost like leaks or connections between the patches that aren't simple flows. It complicates things when you try to define a single, conserved total energy for the whole curved spacetime.
So the curvature itself prevents a simple global conservation law, even though energy flow is balanced locally.
That's the essence of it. And here's the kicker. Noether looked at the continuity equation she derived from the local symmetry of general covariance, and she realized it was mathematically identical to those Bianchi identities Hilbert had found earlier.
No way. The things Hilbert thought were useless because they only worked for an empty universe.
The very same. Noether showed they weren't useless at all. They were the mathematical expression of the local conservation of energy flow, dictated by general covariance. They were the best you could get for energy conservation in general relativity. It wasn't a single conserved number, but a statement about how energy momentum flows consistently through curved spacetime.
So Hilbert had the answer, but didn't see its true meaning until Noether connected it to the local symmetries via her second theorem.
Precisely. She showed that this continuity equation, equivalent to the Bianchi identities, was the correct description of energy's behavior in GR.
That's just incredible. With these two theorems, she explained the origin of conservation laws from symmetry and sorted out the energy puzzle in general relativity.
It was a monumental achievement. Her theorems laid the groundwork for so much of 20th century physics, giving us the tools to understand why things are conserved and how to handle these concepts in theories like general relativity, where space-time itself is dynamic.
It's really a shame she faced so many obstacles and wasn't always given the credit she deserved during her life.
It is tragic. She struggled for years to get a proper paid position. Göttingen eventually made things slightly more official, but then, of course, the Nazis came to power.
And she was dismissed because she was Jewish.
Yes, in 1933, a terrible loss for German science.
But she kept teaching, didn't she, even informally? Shows her dedication.
Absolutely. She held classes in her apartment. Thankfully, colleagues helped her get a position at Bryn Mawr College in the U.S. She continued her work there, influencing a new generation before her death sadly came too soon.
And Einstein's quote about her, it's worth repeating. The most significant creative mathematical genius thus far produced since the higher education of women began.
High praise indeed, and completely earned. Her work wasn't just solving a problem, it fundamentally changed how physicists approached the universe. Focus shifted towards finding the underlying symmetries.
And that approach is still central today. Right. Her ideas live on.
Massively. Physicists took her theorems into the quantum world. They found symmetries in the equations describing fundamental particles. For instance, there is a symmetry related to the quantum phase of an electron.
And Noether's theorem connects that too.
Conservation of electric charge. It's a direct consequence of that symmetry. Her ideas help predict and understand particles like quarks, the Higgs boson. They're crucial for understanding the fundamental forces, even the origin of mass. Her theorems are woven into the fabric of the standard model of particle physics and our search for a theory of everything.
It's amazing. From this specific puzzle about energy and general relativity came these universal tools for understanding conservation laws derived from symmetry. It really makes you think differently about what's fundamental.
It absolutely does. It suggests that maybe some laws we take for granted aren't the deepest level. Maybe they emerge from underlying symmetries of space-time or quantum fields.
So a final thought to leave our listeners mulling over. If conservation laws come from symmetries, and some symmetries, like time symmetry, are broken on a cosmic scale, what other fundamental principles that we assume are fixed might actually be contingent? Might they be emergent properties of some deeper reality, some other symmetries we haven't fully grasped yet?
Exactly. What else might turn out to be not quite as constant or fundamental as we think once we understand the deeper symmetries at play? It's a profound question her work leaves us with.